Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Eric Danianto and my partner Demas Abyan. We are from Material and Metallurgical Institute Technology 10 November. Here, we would like to presentation our paper with title Electrochemical Performance of Nitrogen Doped Carbon with Magnesium Oxide as Composite Supercapacitor Electrode in Aqueous Electrolyte. Here the author Mr. Demas Abyan, Mr. Sutarsis, Mr. Agung Purniawan, Mr. Yusuf Radesar, Mr. Eric Danianto at the Second International Conference on Energy Storage Technology and Application, ICESTA 2022. Here the outline of our presentation: the first, introduction; the second, literature review; the third, methodology; the fourth, result and discussion; the last is summary. Introduction. One of the world concerns today is need for electrical energy associated with vehicles that sell electricity. This is to support global commitment in reduce greenhouse gas emission. It is projected by Ministry of Industry that there will be 38,000 electric vehicles in 2024. With the growth and demand, electricity vehicle has an impact on increasing electricity consumption, which is estimated to reach 2,000 kilowatt-hour in 2025, according to Badan Pusat Statistik. The electric vehicle itself has several types of energy storage, and the main one is the battery. The battery has the characteristic with high energy density but low power density. This effect has decreased the speed of discharging the battery, cause to decrease acceleration of electric vehicle, and have problematic in uphill condition. Another energy storage that can be used is a supercapacitor, which has a high power density but a lower energy density compared to the batteries. In addition, supercapacitor have another advantage like long cycle life, high efficiency, and can be considered friendly to environment. However, the relative low energy density from supercapacitor is still an obstacle so that it effort to increase energy density. Here, research purpose of our paper. The first one is analyzing the effect of adding nitrogen as a dopant to the structure and morphology of the nitrogen activated carbon with magnesium oxide, the supercapacitor. The second is analyzing the effect of adding nitrogen as a dopant on performance supercapacitor. Here's the literature review of our paper. The first one is how to get activated carbon. Here from the pyrolysis method. The pyrolysis method gives our pyrolysis char. From the pyrolysis char is added by potassium hydroxide to increase its surface area and porosity. And then magnesium oxide. Magnesium oxide as metal oxide become a reaction addition again that can be increased capacitance. Addition of pseudo-capacitance properties from supercapacitor. And then there is a polyaniline. Atomic radius from atom nitrogen are similar to atom carbon. This process of substitution nitrogen atom on carbon means that some of the carbon atom in a unit cell are replaced by the other atom nitrogen and having an almost same of radius with substitution from the atom.
Okay, thank you, Eric. Now we go to methodology. For the methodology, we use a pyrolysis process for activating carbon. So the carbon from coconut cell that we got, we impregnated with potassium hydroxide and polyaniline for the nitrogen precursor. For the composition ratio, you can see here for NaC1, NaC2, and NaC3. After that, we mix it with MnO2. MnO2 that we got and process it with hydrothermal and annealing process. And then for the composition ratio is 5 for activated carbon, nitrogen activated carbon, I mean. And then compared to 1 with MnO. After that, we make it slurry with PVDF and carbon black. For the nitrogen active carbon and MnO2 is 8 compared to 1 with PVDF compared to 1 with carbon black. After that, we add NMP and we coat it in nickel foam with 1 times 1 square centimeter of coating. After that, we dry it in vacuum oven. And then for the testing or electrochemical performance testing here, for the powder of mixed NaC1M MnO2, we test it with scanning electron microscope and XRD. And then for the nickel foam that we got before, we use 3-electrode cyclic photometry for the electrochemical performance. Then for the result, you can see here the XRD result that from the activated carbon here to nitrogen activated carbon composition 3, you can see that the peak of carbon is shifted to right. It means that the carbon, nitrogen in the carbon is succeed to dope to activate carbon. And then you can see for the crystal size here. Then after that, after we mix it with MnO, we test with XRD2. Then we can see the MnO phase here. Then MnO that we got is beta MnO2, and then we got Mn3O4 for the NaC3 MnO. And you can see the crystal size of the MnO here. This is Mn3O4, and then MnO2 beta phase. And then we test it with scanning electron microscope. For the scanning electron microscope, we magnify it with 5,000 and then 15,000. For 5,000, it can be seen in structure of NiC1 beta MnO2 that beta MnO2 form, which has a nanoroot shape with size of 600 till 800 nanometer. Whereas in NaC2 and NaC3 here, Mn3O4 has a morphology similar to beta MnO2 but with a different size. As you can see here that the beta MnO2 has a smaller size compared to Mn3O4, which is for Mn3O4 is around 500 nanometer. You can see the compared here that 15,000 magnification of NaC1 MnO compared to 5,000 NaC3 or NaC2 MnO. It's a little, it's a big difference between Mn3O4 and beta MnO2. And then for the cyclic photometry, from cyclic photometry, we can count the specific capacitance, and then we got for with electrolyte Na2SO4 that the specific capacitance, the biggest specific capacitance that we got is for NaC3MnO, which is the composition, the biggest composition of polyaniline. And then it's the same for NaC3MnO. For the NaC3MnO here, we add some potassium iodide to make it bigger for the specific capacitance. You can see here for the graphic too that for the curve, I mean, that the adding of potassium iodide make redox reaction here compared to without potassium iodide. Potassium iodide that we use here is 0.05 molar, and then for the Na2SO4 is 1 molar. Then after that, we varied the voltage to that in 1 volt, you can see the peak here, and in 1.2 volt here, we can see the peak too. It means that the electron is decomposed to decompose, and then it means that the electron is broke. And we know that aqueous electrolyte is decomposed. There is a decomposition of water in 1.23 volt. So it means we cannot have a voltage more than 1.2, 1.2, 1.1 to 1.2 here. And then for the summary, the addition of dopants to the characterization affects the result of XRD, which with the addition of dopants can shift the peak from carbon to the right. However, the morphological results showed no difference. And then the addition of nitrogen dopants in electrochemical testing increased the capacitance, especially at a scan length of 5 millivolt per second. The addition of polyionized nitrogen dopants adds to the active field of active carbon, which increase the maximum capacitance at NaC3MnO, which the result is 167 farad per gram with energy density and pore density 14.9 watt-hour per kilogram and 168.15 watt per kilogram. Thank you for the attention. It's the presentation of our paper. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.